They see me rolling? Okay, cool. All right. Hey, everyone. I'm John, and I'm going to give you a real talk this time, and it's going to be about Haskell. So for those of you who don't know, Haskell is an advanced, purely functional programming language, according to their website, which is all well and good if you know what those mean and if you feel like advanced means anything. So sort of to clarify, of course, here are these attributes of it that people always talk about, which probably clarifies very little for a lot of you. It's statically typed, it's lazy, it's purely functional, concurrent, it features type inference, and a declarative syntax. We'll break it down, and you'll know what these are by the end. So, let's look at some code. So this is a very, very simple Haskell program. All it is there's a module called main, which is very similar to like a Java package or something like that, or actually a Node module as well. And inside of it, we have a main function, which is what's going to execute when we run it, and we print hello world. Hooray, we did it. So what's going on here is, yep, there's the module declaration, the main function, and the function put strlen, which is put string to a new line, and parameter for that function. So you notice the syntax is a little different from your normal parentheses C-style calling, but it's actually ML style if you're interested. So let's take that same program, expand it a little bit, and put some type annotations on things. So similar to Java, where you declare like the return type of your function and the types of the parameters, you do the same thing here in Haskell. So here we have on our function total, which will take the sum of a list. I didn't use sum because sum already exists, and I want the programs to actually compile. What this does is it's a function called total that takes in a list of integers and returns an integer. Pretty simple. Total has one parameter, numbers, and we run fold r with plus 0 and numbers. So the way fold r works is way simpler than you'd think. It's a reducing operation, if you've heard of it called that as well. We take a default number, which is the second parameter, 0, and we apply this function down the list. So we say take the first element in the list and plus 0. Awesome, we get 1. And then we're going to plus that with the second element in the list. And we'll get like whatever, and then we'll get whatever we get from that, which in this case would be 3. And then we'll add the next element in the list to that, which is 6. And then once we're out of lists, we return. And so that's how we get 6 as the return value in this program. It's what's printed out. It's nice and easy. So if you notice, we're passing in a function here, which is just the summing operation. We're going to get used to passing functions around a lot today, so I hope you're ready. So we're going to ignore that type annotation right up there for main. It's just not worth worrying about yet. So that program I had before that didn't have the type annotations still worked, and that's type inference working. It looks at the functions and figures out what types they should be, what types they have to be, and will just compile it anyway. These type annotations are more to keep us sane and to produce errors right where they happen, rather than somewhere down the line if it was inferred and showing up elsewhere. So let's see how far we've come. And you've actually seen a lot of Haskell on the way here. There are no variables. All you have are parameters and constants. So this does some really cool things. Idempotency, for example. If I pass in a function, I pass in a parameter to a function, it will always return the same value for that given parameter, which is really awesome. This is an aspect of referential transparency. But John, what's referential transparency? We're actually going to talk about referential opacity. It's way easier to look at it the other way than it is to look at it like the good way that Haskell gives us. So if you look at these two Python programs, those functions in the program, there's two problems with them. One, in the first one, we are sorting the list and then indexing into it again, which is going to change it. In other words, once I have a reference to list, I can't trust that it's the same value I had when I first got it, which is a lack of variable referential transparency. Over here, we have a function that will return a random element from a list. This is also bad, because if I call that function twice, I don't know if I'm going to get the same value back. This makes it basically untestable and generally just a pain to work with. You can do neither of these things in Haskell, which is a little terrifying. You're like, how do I get random numbers? We'll get there. How do I read from a file? We'll get there. These are all things that we don't want to worry about right now, and we'll get there. So Haskell can do neither of these things the way they're implemented here. And also, isn't that inefficient? If I can't change a value, then I'm going to have copies and different versions of it floating around. And the answer lies in the fact that Haskell is declarative. So when you're dealing with your imperative programming languages, you're telling the computer what to do. You're telling it, do this, do this, do this, do this, and there's abstractions, like, I don't want to have to say, move this register, all of that, but you're telling it what to do. Versus declarative, you're telling it what you want, and you're letting the computer figure out how to give it to you. Algorithms and stuff will be used to sort of help it figure that out, but for the most part, you don't tell it operation, operation, operation. So that's sort of what's going on here. Declarative, what do I want? Imperative, what do I do? You don't have to understand that prime sieve over there, but it's a prime sieve in Haskell, which is pretty cool. What's important to note there, though, is that it looks nothing like this Python program, which you all should be able to understand roughly, which is that I just loop through the numbers, check if they're prime, and then yield them and append them to primes, which is a generator in Python. I figured I'd be fair and make it as close as possible to the Haskell version. But anyway, there's lots of manipulations going on. We're appending into the list things we couldn't do in Haskell and don't want to do in Haskell, because compilers are smarter than you. Much, 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 much smarter. Most people here have run into a problem like, oh, the compiler is just being dumb. Like it's clearly a bug, and then it turns out that no, you just missed something. And yes, that's good for checking purposes and stuff, but the compilers can also do amazing things for performance. So for example, if I append to a list, so I declare a list here of elements 1 through 3, and then append 4 to it, the compiler could be smart and be like, oh, well, it's Haskell. I know that we can't change the old list. So I can actually just append to it in memory and then just not allow references to A to go past element number 3. And so all of a sudden, we're dealing with about the same performance that we would get on a language where we could actually append. But we have protections guaranteed by Haskell. Long story short, you shouldn't care how it's implemented underneath so long as you're algorithmically sound. And speaking of being algorithmically sound, it's way smarter, like way smarter. So let's talk about laziness. And this is where it really shows how smart the Haskell compiler can be. This is all of the Fibonacci numbers in a list. It's done. I don't have to do anything else. I don't have to ask it to give me more values. It's there. It's a list. It's done. And it works sort of like so. So fib starts as 0 and 1, and then we're going to add this big block here. And we'll talk about how this gets calculated. So here's fibs and tail fibs. Tail is everything but the first element. So we start with 0 and 1 and 1. And we add. What zipwith does is it takes two lists, and as it goes down them, applies an operation between the two and produces a new list. So we are adding the first element in fibs and tail fibs to get this new zipwith value. And then that becomes a part of fibs. And it becomes a part of fibs, and a part of fibs. And we've now defined this super elegant, really cool looking Fibonacci sequence. But the problem is the computer will be evaluating this forever because I didn't tell it when to stop or what to do. Thankfully, we actually don't have to have it go on forever because Haskell is lazy. Haskell will say, oh, okay, you can suppose things. You've given me how to understand a list of all Fibonacci numbers, but I'm not going to calculate them until you need them. Until you say that you need these for some purpose, then I will actually go and calculate them for you, which is really cool. You don't waste time. So here, where I say take 5 fibs, it's going to take the first 5 elements and print them almost instantly. Really, really fast, despite us not doing anything fancy to handle any sort of length requirements on our list. Laziness also means that algorithms just become immediately overnight faster and better. So here's a quick sort implementation. Don't worry about it. For those of you who are interested, all it does is it picks the pivot at the start of the list and finds all things less than it and all things greater than it and puts them on either side and then quick sorts it again. It's really cool. Anyway, what happens now is that because Haskell's lazy, when I tell it to quick sort a list, it doesn't actually quick sort a list. It just sort of takes a note and says, yeah, you wanted this quick sorted, and here's how I do it. So now when I ask for the first element, it's actually only going to sort enough to get the first element out of the quick sort, which means that our operation, which was before, n log n, is now n plus k log k, or in this case, O of n. That's the silence of minds being blown, hopefully. But yeah, this is magical. Like, we can use the same implementation over and over and over again, and it just optimizes for our use case, which is so cool. So the problem is, what makes it, actually do things? And the answer is the I/O monad, which is when I print things out, whenever I'm interacting with the outside world, that's when I make something happen, because otherwise it's indistinguishable whether it happened or not. 2 plus 2 doesn't mean anything unless I print it. But we'll come back to that. So, you know, functions are great, but like this would be kind of a pain if this is all we could deal with. It's types. There's those types. We're going to talk about those types now. So, types. There's a lot built in, and we've seen them before. We've used integer. We've used a list of integers. In this type signature we use for this function. So, you know, it's not that weird, but it's going to get weird. So, you can declare types in 3 different ways, 2 of which are shown here. The third is referenced. The first is just the type declaration, which is just for synonyms. I say I have a type name, which is like type string, which is really nice when I just want to have my type signatures be more descriptive. So rather than saying, oh yeah, this takes in a string, is that an ID? Is that a name? Is it your address? It's a function. It's a problem we run into a lot in a lot of languages. We can now just type reference them, and so I now declared my name, which is of type name, and it's equal to a string, which is totally fine. And I can use put strlen, which takes in a string, with a name. It's fine. It's all good. It's all just an alias. New type is used to be a bit more opaque. So basically what it lets me do is, here's a type first name, and first name wraps around a string. What it means more or less is that I can't pass in a first name anywhere I can pass a string. It is a first name. It's sort of like a cheap generic. So that here, for example, I have to unwrap it. So I have first name with an S inside of it, and I can return that S. It's a pattern matching thing. New type, don't worry about it too much. It's not that common, and it's a little more confusing until we dig deeper. And data. Data is the one you're all going to really love. It's super easy. So we can declare things like an enum. We can just say, this is a deck of cards. Well, actually, it's just cards. So we have a suit, which can be either club, diamond, or spade. We have a card value, which can be all the card values. And then we have a card, which contains both a value and a suit. It's a record type. It's super duper simple. By the way, guys, I'm just going to throw this out there. If I lose you, if you're confused, you can ask a question. It's totally cool. Anyway, so when we do this record type, it actually generates functions for us, which, for example, these accessor functions, so I can get the suit of my card, which is important because there's no dot syntax or anything like that. We just have functions and data. So you can also construct it by passing in the value of the suit. Again, this is not rocket science so far. But what about polymorphism? Everyone says polymorphism is super important, generics, blah, 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 like you should be able to reuse code. I don't want to have to declare a new version of equals for everything I declare. Type classes. Type classes are a bit like an abstract class in other languages that you've dealt with. We're going to break down this sort of type class declaration. So this is a class for equality. It's the actual one that Haskell uses. This is the actual implementation, actual declaration of it. So it's class EQ for some type A. This is a type parameter. So think of a generic in Java or C++ if you've seen it before. It's very similar. It's basically exactly the same. So what this means now is we have these 2 functions in the class, which means anything that's any type that's a member of this class, we can use these functions with them. So equals equals takes in 2 elements of the same type that implement equals and returns a Boolean. So I can pass in 2 ints, 2 floats, what have you. And then for not equals is actually defined for us by equals, right? If equals would return false, then we would just return true for not equals, which is why this is the default implementation. So if I want to implement EQ, which we'll do in a second, don't worry, I don't have to implement this because it can be inferred, which is real nice. So this, we're going to get to implementation in a second, I think. So this is type class inheritance. So the idea is some type classes are like larger forms of other ones. So for example, in order to be orderable, ordered actually, I also have to be able to be equated. That's just an aspect of being this. So what we can do is we can extend our equation, our equal type, by adding less than, greater than, and all of those. Which actually, a more succinct definition of this would actually predefine these based on equals, which we could do, but this is just a more simple definition. So this is sort of how we instantiate one of these type classes and how we sort of describe how these types start to relate. So, for example, this is how we implement equals for float. assuming we have a function called float equals, or float eq, that can take two floats and tell us whether or not they're equal, we can then instantiate equals for it by just calling that with the two parameters. This syntax you're seeing here with the two backticks on either side, Haskell allows you to take functions that have two parameters and use them infix if you want to, which is just nice. Like rather than saying float eq x, y, which we could do, we can put it in the middle like we're more used to seeing for things like this. And then here's a similar type signature that's using one of these generic type classes. It takes in equals of some type A and takes in two things of that type A and returns a Boolean. And all it does is just ask for the same, which is really just the same function again, but I figured the type signature was worth seeing. Cool. So there's some really common type classes in Haskell that you'll see all the time. You have equality, ordering, stringify, parsing, all of these you'll see a lot of, especially show. Show is what you use to take any kind of type and display it. Which means by default, you can't show something. You can't print out, one of those card decks we made before because they don't know how to. They're not members of that type class, which is really upsetting because when you can't print what you coded, it's really hard to tell that it worked. So we're going to get to sort of how to make this a little bit easier. There's also integrals and floating, which are excellent for if I want to deal with, for example, non-real numbers. They can fall under those in the proper places. It's real cool. Anyway, so thankfully Haskell provides a feature for deriving type classes, which is that we can simply just say that we want them. A lot of these make a lot of sense. So for example, deriving read. Read is used for actually going the other way. So I can read in a string and get back something of the proper type, which is awesome. So I says, oh, well, yeah, if I read in the string club, then it's going to be a soup, the soup with the value club. And if it's show, I can take the string and just print it back out. Enum, it's one of these. It's equality if they're the same and ordered in the order that I put them in. So that saves me a lot of time and a lot of just effort. Down here, we actually don't get everything for free. For example, they can't be ordered necessarily by default because they're record types. They're not just a single value. But that's okay. We could do that later. So a quick word on monads. Wow, I'm blazing through this. Monads, you'll see them everywhere. Everyone says, Haskell, monads. What are monads like? This is what monads are like. This is it. This is the declaration of monads in Haskell. It is these four methods in a type class. So everyone tries to tell you what they are, like what monads are like. They're just these four functions. And I know I could spend all day digging into exactly how all of them work. But long story short, it's if you can understand what they each mean in the context of the given monad you're using, it's way better than anyone trying to tell you like what's going on there. And now that you all know how type classes work and understand Haskell at a very deep and personal level, you'll be able to just read these things now. But no, I'm actually happy to talk to anyone about different monads. But they're very different. So some common monads that you're going to run into are IO, which is like the big magic one. You'll run into list, maybe, and result a lot. But like lists are monads. Like it's that simple. But yeah, monads. So now that I threw basically all of Haskell at you in 22 minutes, minus me being late, so more like 17, how do you all feel about it? Do you have any questions? Yes.
Are you going to make Haskell submissions to the project coffee cookbook?
Oh, hell yes.
I'll look at time to see.
Oh, it's beautiful. Yeah.
Why do you need monads?
It depends. Monads are, the whole point of monads is for encapsulating behavior. So the idea is, for example, a list. There are list operations that work regardless of what's inside of them. So appending to a list, for example, right? Like, is something that the list really controls and isn't really affected by what type is inside of it. So a list of integers uses the same thing to append another list of integers, or sort of concatenate another list of integers, that a list of floats uses to concatenate another list of floats. It's the exact same logic. All it means is that we want to maintain all of our type signatures, so we just have these monads that sit around and basically sort of handle how to do things. So for example, Foldar, actually, way back at the beginning of the talk, uses monadic aspect of lists, which is, so foldr uses a function called fmap. Fmap allows for the application of a function onto a monad, which basically means if I can say, apply this operation to whatever's inside of you. So I don't know what's inside of you, but here's what I want you to do. So basically foldr says, okay, I'm going to apply whatever x function goes here to all of the elements in the list, which is really cool. So all I do is I say this function has to be defined for whatever's inside the list, whether that's a type int, float, dog, cat, suit, card, whatever. As long as it's defined for that, and this is of the same type as the elements in this list, it'll just work. There's a lot of hand waving and a lot of like not pointing at real things, but that is what it's used for. And yeah, I was trying to stay away from digging into monads too deep, as I think an understanding of how the basics work helps you understand monads better than just diving in and talking about them. Yeah. Any other questions? Yes.
What are some like things that are actually written in
Haskell, for one.
Handoff.
Yeah, pandoc is written. Pandoc, which is a universal system for basically it's like Markdown and HTML and a whole bunch of other things, and LaTeX. It does all of them in one, and it's real cool. People use it a lot of places. Haskell is also used a lot in a lot of the same places you'll see OCaml, places where you need provability. There's a lot of cool things in here. For example, if you, I didn't really point this out explicitly, but there's no null. So nothing that says it's of type integer could ever be null, or nothing that says it's of type x could ever be null, unless I explicitly create a type that includes null, which means that you're a lot safer. And overall, the code is much more testable and much more provably correct. So, banking, you see it in there, trading.
Is there a built-in testing framework?
I want to say yes. I don't know. There's one that everyone uses, and I can't really name it off the top of my head, that does generative testing, which will actually inspect the type signature of your function. I got you next. Oh, yeah.
Quick check?
What?
Quick check? Is that what you're getting at?
I think it might be quick check, yeah. And it will just inspect the type parameters and be like, oh, I can generate values for these and like build tests for you, which is so cool because because of the way the type signatures work. Integer, for example, is actually one of those data declarations. It's equal to 1, 0, 1, 2, 3, 4, 5, 6, and like the whole thing out. So they can just look at these values and be like, oh yeah, it could be one of these things, which is real cool.
You said you told us to get random numbers.
So random, yes. So random is actually under the purview of I/O. Okay, here we go. Let's just do it. Remember I talked about idempotency before. You can never get the same thing back from what you put in. You always get the same thing back when you put the same thing in. And so you can never ask random with no parameters and get something back. And so I/O cheats. I/O is technically pure. If you really want to get into the semantics of it, because what it does is inside of its monadicness, it wraps around a variable, a completely unique value, and what it does is it passes that unique value implicitly into these functions, which means that yeah, I'm getting an idempotent result because I can never duplicate the parameters, which makes I/O hard to test, but I/O is always hard to test. The idea is to have I/O follow the same rules within the language, but at the same time, there's inherent risk in using it for things. Like it just makes testing non-trivial. But yeah, it cheats. And through that, you can think of I/O. This is a cool analogy I heard, and now I'm talking about what monads are like. Which is I/O is a concept of the entire world outside of your program, and whenever you interact with it, you get back a new representative value of that entire world, which means that you can never go back to the way it was. And so I can never, get an idempotent result. I have to always use the newest I/O, which represents the world in a state I don't know, but I know is unique from the state it was before. Yes?
How does it generate? Does that use like microphone input and all that stuff?
Oh, no. Oh, for random?
Yes.
Oh, no. So for random, like most randoms will do in languages, I believe it relies on your OS implementation thread. It may have its own as well, but it's really hard to generate good random without OS level permissions. If you want pseudo random, even then that's built into the chipset usually. So, yeah, that's why it's under I/O. It asks the system what to do. Yes.
So why is this not used more?
It's hard. The issue is there's just so much room for abstraction. Like we talk about abstraction in SE, but like let's be real, an abstract factory has like maybe 3 classes in or whatever. No one really knows what's going on, and there's only 3 classes, and those are implemented from scratch. They don't extend for anything else. But when you start to talk about how some of these more complex monads work, you start to like really have to think like I really need to know this top to bottom, or at least well enough to get going. And so it's not something you want to hand to someone in CS1, even in CS3. You're going to maybe start to show it to them at like the end of, academically anyway, at like the end of their college career. By then they go off into work and work with people who may not have had a full college career in programming and spent most of the time in Java, and that's fine, and they go program Java. Long story short, it's hard, and it requires a lot of mathematical thinking and understanding how anonymous functions work and things like that. It has less real-world analogs than, say, object-oriented programming, which is, a crutch for helping us understand code. Cool. Well, Krishik's gone, but I was going to say it's better than MATLAB. Anyway. Yeah, we're done. That's good. Thanks for coming, guys.
Pretty much anything is better than that. It's so